our first day, and it's a pleasure to introduce you guys to Professor Jorge Matsas, which is definitely local, right? Professor Jorge is from the Institute for Theoretical Physics, and he'll be telling us all about proposals for testing the Schrödinger-Newton equation. So please, Jorge, whenever you're ready.
So thank you very much for the organizers for having me here for this short talk. The title of this talk is Proposal for Testing the Schrödinger-Newton Equation, and this was done in collaboration with my PhD student, Gabriel Aguiar. And let's start with the scientific motivation for doing this work. And we all know that general relativity is the best gravity theory we have up to now. And this is characterized by evolving in a harmonious way space-time and field using classical rules. So here, just for illustration, this is the Einstein equations and a massive scalar field. Very good. So our dream is to replace this classical word by quantum word, right? The problem in such a way that we can evolve everything in a harmonious way using quantum rules. The problem is that we don't have such a theory yet, and you can take two approaches in face of it. One of them is just, try something top-down, like strings or loop quantum gravity or whatever. And a more modest approach is trying something bottom-up. Among these approaches bottom-up, I would like to single out quantum field theory in curved spacetimes. So in quantum field theory in curved spacetimes, you assume a predefined spacetime, and on the top of it, you consider an extra quantum field, and evolve this quantum field on this predefined spacetime. This is, for example, what Hawking did in order to find his famous effect. So he considered the predefined spacetime of a collapsing star into a black hole, and then he realized that as a consequence, observers in the infinite future would extract the particle content of a thermal bath from the state that observers in the infinite past define as being a no particle state, namely the Unruh vacuum. Okay? And I dare to say that quantum field theory in curved spacetimes, in hyperbolic spacetimes, at least for free fields, is as well defined as general relativity. The problem here is that we don't know how to consider the back reaction of these fields on the spacetime. And this is very natural. This is natural because we don't know what is such a thing like a quantum spacetime. So, in face of it, for people like me, who consider myself a quantum field theorist in curved spacetime, I would like to give some contribution in the direction of this very hard problem of considering the impact of quantum fields on the spacetime itself. And one thing that people can think of is adding at the right-hand side of Einstein equations the expectation value of the stress energy momentum tensor of the quantum fields. This is what people generally call semi-classical gravity, and this semi-classical gravity considers a new equation in nature because it's considering this extra term. So new equations have to be tested in laboratories somehow. And the question now then is how to test it. And the most natural way of testing it is, as in general relativity 100 years ago, you go to the weak field approximation and see what new effects you find there before going to something more difficult. So this is precisely what we did. Because when you consider the impact of this extra term in the evolution of one particle state, you end up with an equation which is not a Schrödinger equation. We are in the non-relativist case, but you end up with the so-called Schrödinger-Newton equation. The Schrödinger-Newton equation is Schrödinger's equation with an extra term. This red extra term reflects, reflects this extra term in semi-classical gravity. And what does it say? It says that basically that, an electron in the hydrogen atom would interact with itself through the probability density. This is why we call this is a self-interacting gravitational term, because it's gravitational because of this coupling here, and self because it depends on itself. Okay? So this is clearly much beyond usual quantum theory. Quantum theory says that the probability density is the probability density of finding the electron if and only if you make a measurement. It doesn't say anything about the reality of the electron being spread out all over the space as given by this quantity. So this term goes beyond quantum mechanics, and it has to be tested. In order to give you a feeling about how likely this term is, we should consider this term to be correct or to be realized by nature. Let me replace this equation, this Schrödinger-Newton equation, by its causing, which is the Schrödinger-Coulomb equation. The Schrödinger-Coulomb equation is precisely the same equation, with the only difference that this coupling here is replaced by the Coulomb coupling, by the charge. Okay? And this is what I'm showing you here. Okay? Very good. Now, let's solve it for the hydrogen atom. We know how to solve the Schrödinger equation. We know how to solve the hydrogen atom for the Schrödinger equation, and it's not that difficult to solve it with this extra term. And what we see eventually is that this extra term that would say that the electron would be able to interact with itself via its electromagnetic field spoils completely the spectroscopy of the hydrogen atom. For example, the usual ionization energy, which is about 30-something electron volts, jumps for 1-something electron volts. And this is very easy to understand why this difference. Why it's, at least, it's very easy to understand why it's that easier to ionize the hydrogen atom due to this extra term. If the electron is allowed to interact with itself through this extra potential, I think I run out of battery. But anyway, the potential, by this potential I mean that potential, right? It eventually, effectively, it shields the charge of the nucleus, right? And so it's much easier to ionize the hydrogen atom. So this explains this value. Okay, so it would be very natural to think of, well, okay, this is ruled out by experiment, but perhaps gravity is so different from the electromagnetic field that perhaps nature favors replacing this by the Schrödinger-Newton equation, namely by replacing this term by the previous one, right? So still, we have to test this for gravity, okay? But the problem is that that's not easy to test this for gravity, because you see that the gravitational interaction, as we all know, is much weaker than the electromagnetic interaction. So using the electron atom, the hydrogen atom, to test the Schrödinger-Newton equation is a disaster. Actually, it's awfully difficult to test the Schrödinger-Newton equation with stationary states because of one fact. Because it's very difficult, in general, this external potential that you use to build these stationary states is always, or as far as I know, always, much bigger, much larger than this self-interacting potential. So this leads us to ask the following question. What is the best or the easiest scenario to test the Schrödinger-Newton equation? Which is important in order to say something about the semi-classical Einstein equation. So this drives us to probing the Schrödinger-Newton equation in a Sternard-Gerlach-like experiment because of the following. Because I am going to show you a situation where this external term vanishes, because in a Sternard-Gerlach experiment, when the system is superposed, the system is not under the effect of any external potential, and we can find parameters where even this kinetic term is much smaller than the self-interacting term. In other words, by the way, you can see also this paper, and Grossart's paper came out a little bit later, after ours, but it was published before ours because there was a back and forth with the referee. But both papers, they analyze precisely the same scientific problem, with the difference that we work in different regimes, and when the regimes, we have shown that when we go to the same regime, then the results fit to each other. Okay, so using smart parameters, say one particle state ytterbium crystal, doped in order to have a spin of 1/2, the mass is about 10 to minus 14 kilograms, and the dispersion is this one. And assuming that the distance between the superpositions is about 100 micrometers, then even the even the kinetic term can be neglected. We end up with this very simple equation. The potential is the same. And everything, after all, depends on this time. How long you leave the self-interacting potential to act in order to dephase the superposition, which is not something predicted by quantum mechanics. According to quantum mechanics, you don't have any dephasing, but according to the Schrödinger-Newton equation, you have a dephasing because of this self-interacting term that will depend on how much of this wave function is upwards and how much is downwards. To be a little bit more specific, we consider a Gaussian wave function. This beta term says how much is spin up and how much is spin down. Depending on how much is spin goes upwards and how much goes downwards, the self-interacting potential acts differently upwards and downwards, and you have this dephasing I told you about. Okay? Going directly to the results. These are the results. This is the dephasing. This is the prediction given by quantum mechanics. For example, this is the probability of finding the spin in the x-axis in the positive direction. Okay? For example, just to give you a feeling, suppose that beta is p over 4. If you put here p over 4, you have the same factor here and here. Then the same amount goes upwards and downwards. You don't have any dephasing because of symmetry, and the probability of finding plus x is 100%, because if you have 1 over square root of 2 here, 1 over square root of 2 here, this is 100% in the plus x direction. But if this beta term is different from p over 4, different amounts of the wave function goes upwards and downwards, and you have a signal. Okay? Now let's go to the difficult part. The difficult part has to do with this dephasing. You see, this let it clear that after all, when you want to test quantum gravity effects, you have to phase the Planck mass, the Planck scale. So the closer your mass, here I am assuming 10 to minus 14, the closer this mass is to the Planck scale, the better. But even if you are not that close to the Planck scale, The good news is that you have this factor 10 to 14 that helps a lot. On the other hand, the problem is this time, presently. It's very hard to sustain coherence of such a large masses for times of about 1 second that was assumed here, right? 2 seconds and 4 seconds in order to see a large signal different from quantum mechanics. Okay? But still, I am approaching my 60th anniversary. I still hope that experimentalists are going to make this experiment in my lifetime. So I thank you very much for your presence, and I'm ready for questions.
Questions?
Thank you, Professor. Am I to understand from these pictures that in these formulas, the idea is that whatever the particle or the system is, it will divide itself through the arms, or is like standard quantum mechanics? It's a statistics. Sometimes it goes, sometimes. Because
I mean, this splitting you can just use because you see. Oops. This is for questions. Let me go back. So the self-interacting potential is not important in this region because this part happens very fast.
Okay.
Okay, so this splitting, in order to consider this splitting, you can use plain quantum mechanics.
But in the middle?
In the middle, it evolves according to this equation, right? So you see that according to quantum mechanics, according to quantum mechanics, you would have the kinetic part, right? But here I'm telling you that with these parameters, the kinetic part can be ruled out because it's neglectable in comparison to the self-gravitational potential.
But the self-gravitational is the interaction between the two arms of the wave function.
Not only the two. The wave function, for example, this part of the wave function interacts with this, and that part.
Okay.
So because this distance is large, eventually, this part effectively only interacts with this part, and very, very little with that.
Okay, so now my question.
Yeah.
I know that for experiments we need to have big systems, but conceptually, what would happen with a particle? Like, it would split in two?
No, it would not split in two.
So it wouldn't have this kind of self-interaction?
No, you would have, for example, this was considered by Diozzi. For example, here, this so this was the original idea by Diozzi, which has not to do, I think, as far as I know, it didn't have to do with semi-classical gravity. I'm not completely sure, but I think so. His idea was the following, that if the particle is massive enough, right, it would not spread out. Gravity would hold it, that would be it would, in his mind, approximate a classical particle. Okay, but I'm not advocating this idea here. What? What I'm advocating? That if you want to test semi-classical gravity, which is very popular, the easiest way to do it is to test through the Schrödinger-Newton equation, because this is what you obtain in the weak field approximation. And the way to do it, I think, the best way is via this Stern-Gerlach experiment. Robert?
Yeah, hi, thanks. Interesting talk. So there's a chain of reasoning that gets you to the Schrödinger-Newton equation. So there's an analogous chain of reasoning that gets you to Schrödinger-Coulomb, but then you point out if we believe that equation, it's just doesn't agree with experiment, right? It's like there's an 8% effect that would totally mess up atomic spectroscopy. So what is going wrong? So I have two questions. One is, what's going wrong in the chain of reasoning, do you think? And second, what comes to my mind is to put a parameter in front of the nonlinear part in Schrödinger-Coulomb and set a bound on that. So those are my two questions.
Can you repeat the first one? What goes wrong
Well,
with
the
what?
first one is you say, okay, here's Schrödinger-Newton, let's just replace it with Schrödinger-Coulomb,
Right.
and you get that huge 1.25 thing. So it's an analogous chain of reasoning. It's not agreeing with experiment, therefore something must be wrong in the chain of reasoning that got us to that equation. I'm wondering what you think that would be.
Well,
Like,
I
why isn't it working? That's
Yeah, I think what I would say is that, well, as far as I know, Coulomb thought, well, my answer is the following. This is a completely non-orthodox term that should never appear. Why? Because this is saying the following. This is completely outside quantum mechanics because this is saying that a free particle would be able to interact with itself. This is not completely out of what quantum mechanics tell us. Quantum mechanics tell us that this term, oh, this is failing again.
well, the nonlinear term, presumably.
Yeah, this term just says what's the probability of obtaining the electron somewhere if you make a measurement, but it's not saying that the electron is spread out according to this. So this picture here is compatible with this term, but this is completely different from what quantum mechanics says. Quantum mechanics says the electron, as far, well, to be sincere, what quantum mechanics tell us is that as far as you don't measure the electron is nowhere. It's not everywhere, right? And this term here, this self-interacting potential, would say that, look, the electron is everywhere, according to that. And this goes beyond quantum mechanics.
Okay, that's interesting. I'll think about that. So then the other thing that comes to mind, if we're going to do that, is put in the red term, put a coefficient in front of it, and then turn the problem around to say that I'm going to adjust that coefficient to be tiny enough that I don't have any conflict with spectroscopy. So I'm just wondering if you did that, and if you did, how big that coefficient would be.
I think it would be very, very large, first of all. And this,
Well,
well,
small,
this is very
small.
sorry,
Wouldn't it?
very small, very small. But the most important thing is that it would not be natural in the following sense. This coefficient here, that appears here, says the following, that, look, this electron is characterized by a charge, and this charge interacts with itself through the charge. So, adding some term here, something, well, we could always adjust it, but it would be non-natural.
Well,
You don't have this extra term in the theory, but of course, in an
Well,
experimental way, you could add
sure,
it.
but I fully agree. I mean, I don't want to take up people's time, but I guess I am anyway. I fully agree it would not be natural, but you could argue it should be there because this is new, weird physics, and it will depend on a parameter. So it does seem to me maybe it's worthwhile empirically to just bound this parameter.
I see.
It'll be very tiny, and it's a stinky theory, but so what? We already have unnaturally small things with the electric dipole moment of the neutron, so it wouldn't be the first time. I'm just saying it seems to me that phenomenologically, this is a phenomenological question that as to how big that term is allowed to be given what we know about physics. It'll be tiny, but it's not clear that it absolutely must be zero. That's all I'm saying.
Yeah, I agree. I agree. From an experimental point of view, there could be, well, you can fit with experiments, adding some or multiplying with some small parameter. I completely agree.
Hello, thank you for the talk. I'm an experimentalist, and if I want to do an experiment to look for, say, Schrödinger-Newton correction, would I be looking at semi-classical gravity or low-energy quantum gravity? I just want to know how to distinguish, and how do theorists think about the difference between a semi-classical theory of gravity versus low-energy quantum gravity.
Okay. My answer is I don't know what quantum gravity is, and because of it, I don't know what low-energy quantum gravity is. I don't know. So, a small advertisement. Tomorrow, there will be in archive a paper of ours with Gabriel Aguiar advocating a simple self-decoherence model in which you will see that, in my opinion, or at least in our opinion, there is a Heisenberg cut in such a way that you don't recover classical physics from quantum mechanics. What happens is that when you go out from the Planck scale, depending on the mass of the particle, it comes out quantum or classical, and there is this Heisenberg cut where new physics would appear. So this is an effective view because, in my opinion, nature, the space-time, even considering, the space-time would be, it's not obvious that it would be smooth, for example, right? So I don't have any idea what this quantum gravity is. So the answer to your question is, the Schrödinger-Newton equation, in my opinion, is only testing this equation, whether or not this term makes any sense. So some people have argued that, look, of course this does not make sense in general, but in some cases, when the dispersion is small, it can work. Well, I don't really understand this, because if this is not correct in general, I don't see what happens if the dispersion here is small, of this extra term is small, the error will be small. But still, this equation would be wrong if the Schrödinger-Newton equation doesn't hold. I don't know if I answered your question. My English is poor, and so maybe I misunderstood your question. Did I? Did I answer? Okay.
Questions, guys? Further questions?
One thing that I don't understand about this kind of formalism, in the gravitational potential, you define it as an integral over psi squared, right? So, but what is psi is a solution of the Schrödinger equation.
Right.
So what
this is a non-linear equation.
But you're plugging in the solution of the Schrödinger equation without the Newton, and then you...
No. This has to be solved in a self-consistent way. This equation has to be solved in a self-consistent way with psi here. This makes, of course, the calculation much more difficult because this is nonlinear. But still, this is a nonlinear equation, it can be solved. Okay? So think of Bose-Einstein condensates.
More questions?
Okay, so do you think this self-interacting term could be somehow interpreted in terms of the Kerr term of nonlinear optics, quantum optics, for example, nonlinear optics, where you have like psi squared psi as a nonlinear term in the propagation of a pulse, for example, and then do you think that this model could be somehow studied analogously through a model in nonlinear optics?
I don't know. To be sincere, I have nothing to say about this.
But have you? That's maybe it's a
It had
possibility.
better I don't speculate about something I don't know.
Oh, okay.
Okay, I'm sorry.
Further questions? Well, if not, so let's thank the speaker again.
Thank you.
Okay, guys, so we resume our activities tomorrow morning at 9 a.m. sharp, right? So see you there.